So I'm representing a startup, which is actually located here in Amsterdam, where we're developing a radically novel approach or process for microfabrication, which, well, with the idea of actually enabling really fast fabrication, enabling serial production of microstructures. Original idea is inspired by X-ray tomography and kind of combined with stereolithography. As a reminder, tomography is basically about creating many projections of an object and then computing the 3D image that generated these projections. Well, stereolithography you're probably familiar with. That original idea, we actually patented at the Institute of Mathematics and Computer Science in Amsterdam. And then the same year, we realized that the same work is done by guys at UC Berkeley. And they published a really nice work about it. It's called computed axial lithography. And basically, the idea is that you generate multiple projections. You are projecting them into a photosensitive medium, and that creates a 3D shape volumetrically without touching it, without without going layer by layer. So it can allow you to generate structures extremely fast, but it doesn't work at the micron scale. Which we of course want to do, because if we look at all these different 3D printing technologies, their speed versus resolution, if you're in the area of about 1 micron, then you pretty much only have 2-photon lithography, and it does have a limit on speed, although it improved a lot in the last 10 years or so. Now, we've seen already images from nanoscribe. I always give them an example that we see very exciting developments using 2-photon lithography. They have impacts across very different industries. And we would like to then enable kind of the next step, which is how do we mass produce some of these structures without having to replicate them using a different technology. We started developing our methods around 2019, starting with just an idea, which was patented. And then 2021, we had one of the first proof of concept setups, then followed up with a prototype, and then some prints starting last year and this year. I have to say that we did very little so far in photonics and optics. We started with different applications, and I'm going to show you some examples. And we are actually looking into, okay, what can we do in optics and photonics next? First of all, what is the process? So this is stereolithography. You are basically illuminating photopolymer at the surface. You're using a single photon chemistry to polymerize layer by layer. It has a limitation on resolution and speed. Then, if you want to break it, you go to 2-photon lithography, which uses a 2-photon process to polymerize material point by point inside a volume. Now, what we do is, again, a single photon process where we are generating a stack of projections that are focused at different depth inside a photopolymer. Because now it doesn't have an advantage of localizing reaction through a 2-photon process, we're actually using an alternative principle, which is a dual-wavelength principle, where second wavelength is stopping a reaction or inhibiting the reaction. And then we have a computer model that can follow forward model, and it can calculate the inverse problem for what happens if you're projecting a stack of patterns of different wavelengths throughout the whole volume, and how do you get a certain 3D shape by doing that. It is possible to do, again, because of this dual wavelength chemistry, because we put a lot of effort into calibrating quite an extensive computer model of chemical reaction and of the optical light propagation through the resin. We have a prototype here in Amsterdam, and we have another prototype in Eindhoven. So you're very welcome to come and check it out. And if you have any ideas how to use it, I will be very happy. So far, that was actually one of the first examples we've shown, which was calculating this simple structure of this kind of a simple wood pile, and then printing it, which was real time a few years ago already. Then we focused on specific projects. Our first project was in microneedle array patch technology. For those who are unfamiliar with it, it's basically idea is that you have a patch similar to nicotine patch with microscopic needles that allows you to vaccinate yourself or to deliver drugs. The tricky part about these structures is that they're relatively large. I mean, the needles are typically about 1 millimeter in height. They have features of, let's say, a micron or so. And while mostly they are produced using mass production techniques like embossing or molding, there were a lot of academic works that show that 3D printing can be really advantageous here because you're creating structures that can allow you to control the time of delivery or the volume of the vaccine that is transmitted through these needles, but then they're almost always impossible to replicate. So it would be great if you can just directly print these structures, but really fast. Here is a real-time video of kind of a benchmark example that we made with a simple cone-shaped needles, 0.5 millimeter tall. This area is about 1 by 1 millimeter, and then we are completing. We can complete about 1 centimeter of these type of structures in a few minutes here using our lab prototype. And we expect that in the future generation machines, or let's say the actual MVP that we want to build, it will be at least 10 to 20 times faster. We've printed a number of microneedle designs for our partners and academic partners as well. We've compared it to a work which was published by Carbon 3D and Georgia Institute in 2022. And we could show that we are already about 10 times faster. And as an extrapolation, like I said, I believe that this technique could be fast enough to actually mass produce microneedle patches. We've had a number of other projects that some of them I can show, which here is kind of a simple bioscaffold. What is important about it is that it has overhangs, so it's not just a kind of a 2D or 2.5D structure. We've managed to make multiple projects around cell capture and analysis or cell filtration with kind of a multi-layer, multi-scale membranes, which is something that we recently finished. And right now we are looking across these different fields. We're also looking at first use cases that we're trying to do in optics and photonics. Here I hope that I can find people with new ideas of what we can do. It's important for us to kind of find a good balance between, say, low-hanging fruits that we could start with and something that actually delivers value to, the videos should run, delivers value to the user. So happy to talk to you after this talk. Thank you very much.
Thank you.